Welcome to this presentation. In this model, I am going to speak about insulin pumps. The drug infusion systems basically consist of two components: a mechanism that delivers the medicine and the means of controlling the rate of delivery. In open loop systems, the rate of delivery is set by the nurse or physician on the basis of past experience, mathematical computation, or by trial and error. The fluid is delivered at the set rate until the setting is changed. But in closed loop systems, the effect of the drugs are monitored by the appropriate transducers and the desired delivery rate is computed and set automatically. The pump operates in such a way to keep the physiological variables as close as possible to the desired value. As an example of closed loop system, we can say that the use of controlled infusion of the drug sodium nitroprusside for the control of the blood pressure. A pressure transducer measures the blood pressure and this information is sent to the control algorithm which determines the rate at which the drug is infused into the patient. And this is obviously a more effective method of controlling the blood pressure as compared to the manual control using the same chemical agent. The traditional and simplest intravenous infusion system consists of a fluid container, administration set, and a clamp to control the flow from the set to the patient. The driving pressure is the difference between the hydrostatic pressure generated by the column of liquid in the administration set and the venous pressure. Since the latter is typically 4 to 8 mmHg, the driving pressure is approximated by the level of reservoir, usually adjusted to be 60 to 100 cm above the patient. Infusion into an artery would require raising the reservoir to some 2 meters, making this method of intra-arterial infusion impractical. And the major difficulty with traditional intravenous infusion system is that the flow rate cannot be accurately controlled. The flow rate is counted in drops rather than measured volumetrically. The rate is difficult to adjust, and even if adjusted correctly at first, it will change with time. Intravenous controllers are mechanical or electrical devices that automatically control the flow rate of fluids, even though the driving pressure is still generated by gravity. These sets contain chambers and valves that meter the fixed volume of liquid for infusion. The devices generally raise an alarm where malfunctions such as empty container, occlusion, and low batter are detected. Infusion pumps, rather than depending on gravity to generate flow, develop pressure by one of several electromechanical means. And mainly two methods will be used. One is syringe pipe, and in syringe pipe a motor and through a gear reducing mechanism and a lead screw applies force to the plunger of a syringe containing the drug. So the device is mainly convenient for the applications that require the delivery of volumes limited by the syringe size. Syringe pumps are usually of a reciprocating type. A plunger or piston delivers the fixed volume of fluid on each stroke. So they require valves or normally furnish a pulsating flow which can be evened out by the use of reservoirs and by polyplex arrangements in which discharge portions of the stroking cycle is spread over more than conventional 180 degrees. Piston pumps can be used at high pressures, and control is achieved by varying the stroke length or the stroke rate. And the second category is peristaltic pumps. These pumps squeeze a flexible bag or tube to produce movement of the liquid inside the compressed container. Linear peristaltic pumps have a row of fingers that compresses the tube in wave-like motion and squeezing out the liquid as the wave propagates. And the often used rotary peristaltic pumps use a rotor that pushes rollers against a tube along a semicircular path. These pumps have the advantage that the fluid doesn't come into contact with the pump, avoiding contamination. If true volumetric pumps are required, and however, special tubing must be used. So the various means of achieving peristaltic actions are cam-operated fingers, pressing the tubes in succession, and a rotor on eccentric shaft which squeezes an eccentric cylindrical linear, and a row of eccentric cams which moves the cam follower, producing a clamping effect and imparting squeezing action to plastic tubing, among others. They are self-priming as no values or seals are required and the accuracy rate is high. So peristaltic pumps use the speed control of the device motor, which may be a synchronous electric motor. So insulin pumps are mostly used for diabetes. That is, people with diabetes cannot make their own insulin, a hormone that is normally secreted by pancreas. So insulin is essential to metabolize sugar and hence generate energy. Currently, most diabetes inject insulin 2 or more times per day, with the dose injected based on the readings of their blood sugar level. The personal insulin pump is an external device that mimics the function of the pancreas. It uses an embedded sensor to measure the blood sugar level at periodic intervals and then injects the insulin into the to maintain the blood sugar at a normal level. So it is also known as continuous subcutaneous infusion therapy. And this diagram shows the insulin pump methodology. Insulin pump is nothing but artificial pancreas. By this, it is meant that a device which consists of a blood sugar sensor, a computer, and an insulin pump, and such a system would bypass the body's own pancreas. However, the development of the glucose sensor is probably the most difficult component of the system. And there have been intensive research to develop artificial pancreas which is called insulin pump. By this, it is meant a device which consists of a blood sugar sensor, computer, and an insulin pump. This more practical approach can be followed to develop a program-controlled insulin pump. This pump delivers the insulin through a catheter inserted into the body. The device can deliver insulin in two ways. One is fixed program unit with a preset of 24-hour rate per time profile, and the demand program unit with which a based rate is pre-selected and a supplementary dose is triggered at meal times. An external program controlled portable insulin dosage device is described by Frankels at 1981, and the device has some features like it should be possible to wear the device in comfort for long periods and under all normal living conditions inside and outside the clinic. Right, and the patient should be able to go about his normal work. It must be easy and safe to operate both by the physician and by the patient. All infusion pumps should be possible and practicable, including intravenous and peritoneal and intramuscular. The pump must have sufficient supply pressure to reserve to prevent possible catheter clogging through microthromby. And the highest possible level of patient safety must be assured. Malfunction of the device must be excluded as far as possible or must be signaled immediately to the patient and must never lead to dangerous overdosing. So, in order to fulfill these requirements, a stepper motor driven roller pump with a swing out counter jaws is employed as a pump. The device is of the demand type on a preset basal rate. A supplementary dose of insulin of selectable sizes is called up by the patient at meal times. The supplementary dose is administered as a rectangular rate profile with variable time or amplitude. The insulin reservoir consists of a collapsible laminated foil bag and forms a one-trip particle together with the attached silicone pump tubing. The catheter can be connected to a pump tubing with a standard lure connector. The number of alarm and safety circuits ensure that a dangerous condition cannot occur. In the case of failure of a system component which would lead to unintentional overdosing, the pump is automatically switched off and an acoustical signal is triggered. And the reservoir is nothing but a plastic cartridge which holds the insulin that is locked into the insulin pump. It comes with a transfer cord that assists the pulling the insulin from the reservoir. The reservoir can hold up to 300 units of insulin and is charged every 2 to 3 days. An infusion set includes a thin tube that goes from the reservoir to the infusion site on your body, and the cannula is inserted with a small needle that is removed after it is in place. It goes into the sides of your body similar to where you give the insulation injection, and the infusion set is changed every 2 to 3 days. The infusion set is placed into the insertion device and with the push button, and the infusion set is inserted quickly and easily. As I said earlier, the set should have the following features which I have already mentioned. Okay, and the insulin reservoir consists of a collapsible laminated foil bag and it forms one drip particle together with the attached silicone pump tubing. Okay, and the catheter can be connected to a pump tubing and with a standard connector. And a very important parameter in such pumps is the accuracy of the pump delivery rate, which refers to the average rate per complete revolution of the pumping head. The delivery rate is influenced by electronic component tolerances and drifts, which can be limited to plus or minus 0.5% and by proper selection of components. Manufacturing tolerances of the pumping head, which can be limited to plus or minus 1% with the proper pre-production control. And manufacturing tolerances of the pump tubing, the internal diameter, wall thickness and hardness of the pump tubing have an effect of supply rate. The error caused by the tubing could be of the order of plus or minus 4%. So these errors are usually tolerable in patient treatment since an individual dose is determined with a particular dosing device and a particular tubing. Thank you.